In this video, let's talk about the standard error of the mean and its application. Standard of the mean is super important because it gives us some idea how two groups behave due to the independent variable. So let's take a scenario. We have 30 onion bulbs, and we want to figure out if coffee in the water or a hormone gibberellin in the water would affect the growth of the root cells in the onion. So we have the onions, let the roots, the tiny roots hang in the control group. The control is negative control at this point, just plain, the roots are hanging into plain distilled water, nothing else. The other water contains coffee, a little bit of coffee, and another one contains gibberellin. It's a hormone, plant hormone that supposedly do growth and whatever. So doesn't matter at this point. We place 10 bulbs in water, 10 bulbs in the coffee water, and gibberellin in the third one. After a certain day, let's say 2 weeks, we measure the length, the longest the length of the root, and we make an average growth out of the 10 data points. And for the control, it's we notice that the average is 20.5 millimeter, the growth from day 0 to day, let's say 14. The roots, the onions, that their root were suspended in the coffee, they grew different, 22.7, and the average for gibberellin was 22.8. We figured out the standard deviation from the data, how far these normal data points are from the average. And we got 2.8 in here, 4.8 for the coffee. 4.8 means that the data is pretty scattered, more scattered, wider range than compared to the control or the hormone gibberellin. We try to figure out the standard error of the mean. What is standard error of the mean? So we have a small sample size, or actually a sample size, 10 samples, and we want to extrapolate that for the entire onion population on the world. We cannot do that because it's impossible to do that, but we aim and we try to figure out where would the true mean be based on that data. So the standard error of the mean, please use the formula as standard deviation divided by the square root of the sample size. We said that the sample size for our case, n equals 10. So say a standard error of the mean, 2.8 divided by the square root of the sample size, and altogether 2.8 divided by square root of 10 equals to 0.89 with a little bit of rounding. And you do the same for the coffee water, and that will be 1.52. You will do the gibberellin one on your own. The standard error of the mean. We usually have two standard error of the means that gives us 95% confidence about our prediction based on the effectiveness, the difference between the different independent variables. So this gives us 95% confidence. It's pretty confident. It's a good value to be confident with that. So what we do is we time the standard error mean, this value 0.89, and we will get 1.77 for that. If we time that number by 2, we will get 3.04. We will figure out for the gibberellin. Now, the values, so let's start to graph. The x-axis is usually for the independent variable. These are our groups. And the y-axis is going to be the dependent variable, what we measure. The dependent variable, well, I will make a discontinuous sign in here. So that means we start the numbering at here. So this will be 18, 20 millimeters, 22, 24. Please do not forget to label the y-axis. That is the dependent variable. So the average growth. And put the unit millimeter in parentheses. That we measure that in here, millimeters. Now the title will be the average growth of average growth of root, onion root in different media with plus minus 2 standard error of the mean. So we will plot those values too. So let's start with the control, and the control's average growth is 20.5. So we will go 20.5, so it will be here somewhere. It's a bar graph. So that is the value for the average. And I will add plus 2 SEM. This value 177 to 20.5. So it's altogether will be 22.3. And also I will subtract 2 SEM from the mean. That means plus 2 SEM and minus 2 SEM. The minus 2 SEM will give me a value 18.7. Now, let's do and graph that. 22.3 is here somewhere, and 18.7 is here somewhere. We can connect the two lines, and this will be the error bar for the control group. It means that the true value of the average growth for the control group can be here, can be there, can be here, there. If we extrapolate this average in the experiment, the average to the entire population. So that is the error bar for that. We are 95% confident that the true value would be between those two lines along the error bar. The other group is the coffee group. And we do the same, 3.4 plus 22.7, and it gives us 25.8. And we subtract the 2 SEM from 22.7, and this will give us 19.6. We do the same with the coffee. The average value is 22.7, 22.7. I'm doing fine. I'm just recording a lecture. 22.7. So here is 22.7. Here is this. And we add to SME to it, 25.8. 25.8 would be here, and 19.6 is going to be here. So this is the error bar. Check that. This is a little bit wider because the standard deviation for our sample was wider. So this really leads us to see that the true value can be really wide in a wider range. Now, what does it mean? If we check this and check that, this is an overlapping area. So the true mean for the control, for the negative control can be here. And the true value for the mean for the coffee can be here. And that means that they would be here too. So it would not really make any difference if we use coffee for helping germination or not for the onion roots. Because the two error bars overlap with each other, that's why there's no significant difference between the independent variable's effect on the dependent variable. We are 95% confident with that. Please do for the gibberellin on your own and check if the error bars are overlapping or not. If they overlap at one point, that means there's no significant difference and you are 95% confident with that. If they don't overlap, that means you are 95% confident that that the independent variable affects the dependent variable because there's a difference in the two means. How about that? Have a good day.